even though there is no and I'll be speaking about embedded surfaces in alternating links, other links, and other three manifolds. So you might notice that the title is a bit long, and really what I want to talk about is about maybe evolution of techniques and how they develop and how something for a small family can inform something bigger. So to start, manifolds in low dimensions, 2, 3, 4, are often studied through their submanifolds, and very often we study submanifolds of codimension 1. So, for example, for 4 manifolds, there is a study of trisections. For surfaces, we often study curves. And then for 3 manifolds, of course, a lot of the study of 3 manifolds has been informed by the study of embedded essential surfaces. This goes back to 60s to people like Pekin and others. And in particular, if you look at one particular family of manifolds, and these are alternating link complements in 3-sphere, their study actually was very much advanced by study of embedded essential surfaces. So many fundamental facts about them were proved using essential embedded surfaces. So I'd like to maybe try to less or more quickly look at those historical results, but also look at how they inform our study of links more generally. And eventually I'll be talking about links that are not alternating anymore, that do not lie in 3-sphere anymore. And in fact, once we talk a bit about cusp 3 manifolds, I'd like to talk about hyperbolic 3 manifolds, all hyperbolic 3 manifolds close to cusp, and how some results got intuition from this initial study of just alternating links in 3 spheres and embedded surfaces there. So I want to start by recalling some maybe historic theorems about alternating links. So let me say some historic theorems. About alternating links. And I guess to me it feels like almost a breakthrough was made maybe in 80s, 90s in the study of alternating links. And this perhaps started with Minescu's work on alternating links. So this is Minescu and 82. He proved that non-split alternating link with a prime diagram is prime, right? And this was proved using surfaces, embedded surfaces, so no non-split alternating link with a prime diagram. Is prime. So this goes back to Minescu's thesis. And then you can talk about many applications, but one of them, back then there was no SNAPI, even SNAPI, I think, was only in the works. And you could use this to see which links are hyperbolic out of alternating links. So Thurston proves that whenever you have a link, you get satellite link, or you get torus link, or you get hyperbolic link, roughly. And so this is due to Thurston. And then if you got an alternating diagram, which is reduced, then and prime, then what you knew, if the link is prime, the diagram must look prime. And for satellites, the diagram will not be prime. So very quickly you knew, okay, this is not that just by looking at an alternating diagram. For torus, it must be 2n torus. So, these diagrams are very special. They look like this. And you just wind n times around the torus. And you knew that whenever your diagram did look prime, was alternating, and was not a diagram of 2n torus link, it had to be hyperbolic. So everything else really fell here. And you immediately, just from alternating prime diagram, could see if the link is hyperbolic or not. And of course, you still can do it. So this theorem was, rather interesting, especially before we could run SNAPI and do all these things But it was not the only interesting thing that was proved about alternating links using surfaces. Here's another one, again, just to do a bit of a review. So this goes back to Menasco, 82, and some results. It was pushed further by Tsvietkova in, I think, 91. So every essential Conway sphere, so here we're looking at punctured spheres. So every essential Conway sphere in a prime alternating link is either visible or hidden. And this is visible or hidden. Again, these were ways in which these spheres manifested themselves as curves, possible curves in a link diagram. So those of you who are familiar with standard position for surfaces know that visible is perhaps knows is something where you can draw just a curve intersecting link diagram 4 times. It's called PPP curve, or hidden is where you can draw 2 curves kind of going through saddle. Saddle is at a crossing, puncture is at an edge, saddle puncture. So this really was classification of, you can think of this as genus 2 surfaces or as essential 4 punctured spheres. And it also had quite a few applications. So if you're not theorist, you want to know how to distinguish rational tangles, how to distinguish rational links from non-rational links. And it turned out that if they're alternating, you just see it right away. You see it from the diagram. So let me write this application, just one of them. So rational links and tangles were just obvious from the diagram. Rational links, tangles, and basically they don't look like anything else, but rational tangles are, let's say, obvious from the diagram. Whenever your diagram is reduced alternating diagram. And also an application that we worked on later was that you can also see that prime tangle decomposition is kind of obvious. So prime tangle decomposition. And by the way, this was, I should say, about rational tangles, this was work of Tsvietkova. I think it goes to also 91. And then prime tangle decomposition. So decomposing your link into prime tangles, this is something was asked back in the day by Licorice and Kirby. What if knots and links are built from those kind of building blocks called prime tangles? So prime tangle decomposition is also visible from an alternating diagram. So this is also maybe pushing this theorem further, and this later work by us. So this is with Joel Hess, Abby Thompson, and I think it was 19. And these are just some applications of these classical, I think, theorems, classical and knot theory. And what's interesting is that their proof is based on something called standard position for surfaces. So many of you might have used it, but possibly not all. So proofs are based on standard position for surfaces. And this standard position is a method that was developed in Menasco's work back in his thesis. And really, very basically, what it means is that the surface is transverse to a projection surface. So the surface that is embedded, in a way, you can say that it's almost transverse to a link diagram. So it's actually transverse almost everywhere except for at crossings. And then at crossings, it described how it intersects the link or the diagram. So proofs are based on standard position for surfaces and maybe I should say transversality for transversality for a surface to a link diagram. And this, of course, is also reminiscent of standard position, right? So in 60s, he can develop standard position for surfaces, except for, so I'll write this, reminiscent to normal surfaces. So normal surfaces are also based on transversality, except for your transversality is to the triangulation of a three manifold and not to link diagram, right? It's not necessarily in cusp manifolds, you can use it in closed manifolds. And both of these techniques, informs the study of three manifolds in a profound way. And let me maybe just mention some other consequences and maybe theorems that were proved and applications of standard position. So some other applications, maybe more recent. Some other applications of standard position for surfaces. One of them, something I guess we'll know about, is tight flapping conjecture, right? And Tate had several conjectures. One of them was specifically about getting from one reduced alternating diagram to another by a sequence of flaps. And this was proved by Manasco and Tsvietkova. They actually used several different techniques, but one of them was very similar to standard position. So they took checkerboard surfaces and put them into something like standard position. So made them almost transverse to a diagram. And this, I think this is also 91. And maybe let me use this to quickly advertise a related result with a student, even though it's not directly related to standard position, but it's using tight flapping conjecture. So this is 24. Basically, what it implies, if you think hard enough, is that whenever you want to recognize, whenever you want to check equivalence of alternating links. So you have two diagrams, alternating diagrams, and you just want to check whether they represent alternating links, which are the same or not. You actually have a polynomial algorithm. So this heavily uses tight flapping conjecture. It's not a direct corollary, because first you have to know that you have only limited number of flaps. Something tight flapping conjecture doesn't immediately tell you. But even, if you have polynomially many flaps, still to make all sequences of those flaps would take exponential time. So it's not a direct consequences. You have to work a bit more. But in particular, those classical results can be used to prove that alternating link recognition is just has polynomial time. We still don't know, by the way, how fast is link recognition in general, right? Or even unknown recognition in general is still kind of tricky question, because some things proved, but not everything proved. So some other applications of tight flapping conjecture, also going kind of back in time, cabling conjecture for alternating nodes was proved in 92 by, so cabling conjecture for alternating nodes also was proved using standard position for surfaces with boundary, and this was Manasco and Tsvietkova. And then later results about number of surfaces, maybe let me call it, maybe I won't call it anything. So just theorem in 2015 with Haas and Thompson. And it establishes a polynomial bound for an alternating link for number of closed essential surfaces of genus V. So number of closed essential surfaces of genus G is at most, and what we have is constant C sub G. So this constant, it's actually a function of G, but once you fix G, it's a constant. And then N, where N is number of crossings to the 40G squared. So N crossing number of crossings. So what was maybe new about this bound? It was just for alternating links, and the point, alternating links in Tsvietkova, but it was the first polynomial bound. So you see it's polynomial in terms of number of crossings. It was also the first bound that was universal and explicit. So we didn't say, there exists a mysterious constant, or maybe there exists a mysterious function such that it bounds. Now, actually, CG is explicit. You can write a formula in terms of G. So that's the only reason. I did not write it in full is just because it's bulky. But basically, we know what it is. So so this happens to be universal also in the sense that it's the same formula for all alternating links, right? It doesn't change link by link. And that's what was new here, because before we had bounds by people, other people. For example, you could take normal surface theory, and normal surface theory gives you exponential bound. So normal surface theory, you triangulate link complement, and you get e to the e to the e to the e, and then some function of G. So it was a tower of exponentials. There were also better bounds by Kan-Markovich. Going back to, I think, 2012, and they were very general, so very general class. So for any hyperbolic three manifold, but they had to say, there exist constants, because it would be harder to do them explicitly. So for any manifold, there exists its own two constants, and then the bounds are, you get Cm G to the 2G as a lower bound, and then here you get upper bound with capital Cm, same way. So what's different here is, on one hand, of course, you have a very general family of manifolds, but on the other hand, you get exponential bound with some constants, right, that change from manifold to manifold. So you don't get this benefit of being universal or explicit as you can for alternating links. And so this first theorem was for closed surfaces. There also was a theorem for sacred surfaces. Maybe I should call it theorem 1, theorem 2. So theorem 2, same people, was 2018. In a way, same theorem, except for you now look at sacred surfaces, and it actually can be also generalized to spanning surfaces, so not necessarily orientable. And the bound is for n, again, n is the number of crossings, 64G squared minus 48G. So again, you get polynomial universal explicit bound for sacred surfaces or spanning surfaces. And all of this also use standard position. So the point of mentioning the theorems is not just maybe even to talk about the theorems themselves, but to say that, you see, standard position allows us all this. 7 years later, we still can prove theorems. And we used some geometry in addition to standard position, but it was still perhaps the key technique in these bounds. So, and of course, what was special about standard position was that it was limited to alternating links in three-sphere. So something I want to maybe talk about today is that it turns out that you can actually generalize this position, generalize this technique, and do something similar, first of all, for cusp manifolds that are complements of links satisfying some restrictions, but in arbitrary manifolds. but also you can actually push this further and find some kind of analog of this in hyperbolic stream manifolds, mixing it with some geometry and some and normal surfaces. So we started working on this with Jessica Purcell first. So part of what I want to talk about is joint work with her. And this is 2022. And what we proved, it doesn't really sound like a good theorem, but it was actually hard to prove. So standard position for surfaces works if you apply it in something called weakly generalized alternating links. So there was a long paper which was just about the technique. So standard position for surfaces. And I'll talk a bit about these manifolds themselves, but this is a very wide family. We're not talking about links anymore in three-sphere. We're not talking about just alternating links anymore. So standard position for surfaces generalizes to and this is called weakly generalized alternating links. I'll abbreviate them as VGAL. Go. And what these are, so we want to go beyond three-sphere, and of course we're not the first ones. So some of these families, for example, are toroidally alternating links. So you take thickened torus, toroidally alternating links, and you look at links that are alternating on the torus and say thickened torus. Virtual alternating links are there. Some other links, you can take alternating links in three-sphere, but you can also take many non-alternating links in three-sphere, and they also will be in this family. Because now you will be allowed to project not just on two-sphere, but on any embedded surface, pretty much. And we're not the first to study these families of links. I'm meeting some results I might have talked about otherwise, just because this talk is not infinite. So there were people who studied toroidal alternating links before us, virtual alternating links before us. Also various generalizations of links in various manifolds, but link complements in various manifolds. But what is happening here is that we want to take one of the maybe most general families that we can, that includes all these, and develop a very strong technique for it that will apply to all of them. So what I want to do now is to try to switch to slides, because my statements will now get more and more long, maybe, and complicated, so it will be easier to read them rather than write them on the board. So let me do this. Okay, so hopefully you see my slides. And let me think. All right, so what is this mysterious family, this weakly generalized alternating links? And this goes back to Hovey and Purcell. So actually back to Josh Hovey's thesis, but also his work with Jessica Purcell. So instead of considering links in three-sphere, we are considering now link in a compact, orientable, irreducible manifold. And your manifold may or may not have boundary, up to you. And then we used to project links on plane or two-sphere. Now what we do instead, we take close-oriented embedded surface as projection surface. This surface doesn't even have to be incompressible, so it can be a pretty strange surface, just floating there. And we used to require, like all the Minasco's work and standard position, classical standard position requires that the projection of a link is alternating, prime, non-split. So we do say, okay, we need our link project on that surface in an alternating way, in a prime way, so there is a generalization of prime in a non-split way, and we also want the projection to be checkerboard colorable. And you say, all right, once you took your manifold, you took your link, if there is some surface where such a projection exists, you got yourself weakly generalized alternating link. And of course, this gives you a lot of options. Even in three-sphere, you can take a non-alternating link and project it on something that is not a two-sphere, get an alternating projection, and then this is weakly generalized alternating link, even though in classical sense, it's not alternating. And of course, links in thickened surfaces work here, links in projected on handle bodies, Hilbert surfaces, and all kinds of things. So this extra condition that the checkerboard colorable ensures that your diagram is not too strange. So you see here two pictures. On my left, we see non-checkerboard colorable picture. On the right, we see checkerboard colorable picture. And non-checkerboard colorable will be difficult. So these are actually links on tori. Each of them is projected on the torus. So that's why identifications. So once you glue this, there is no way to checkerboard color it. And that link would be hard to work with. So we don't consider these weakly generalized alternating. And so what happens here, it turns out that many theorems that I talked about hold. And the fact that they hold is almost like a simple corollary once you develop this standard position. So I talked, for example, about non-split prime diagrams representing prime links. This is the very first result I started with, given by Menasco. And it turns out it holds immediately for these links once you develop standard position. And as a result, I talked about was, well, I mean, you can form this, okay, split links being split, prime links being prime, and there's two theorems, but and as a result, I talked about was Conway spheres. How do you represent Conway spheres? Any Conway sphere is either visible or hidden. So this goes back to Menasco and Thistlethwaite. Again, this almost immediately, you get this as a corollary of standard position in alternating links in three-sphere. So once you developed your standard position for weakly generalized alternating links, it holds for weakly generalized alternating links as well. So many of these classical results that I talked about now become a simple corollary once you develop a standard position for weakly generalized alternating links. We also get bounds to hold. This is not a simple corollary anymore. This is something where you need to put some work in to find an analog. However, you still get universal and polynomial bounds using standard position for weakly generalized alternating links. And here's the theorem, here's the analog. It gets slightly more complicated because your manifold gets more complicated. So in addition to involving things like crossing number and things like genus of the surface, you also have to now think about the structure of your manifold, because when you decompose link in three-sphere just by in two balls, one above the projection plane and one below the projection plane, you just have a very simple topology above and below your diagram. Here, however, you don't anymore have simple topology. Oops, I'm sorry. And something you have to think about is what happens if you take the complement of your projection surface out of your manifold. So if your projection surface is thickened, it decomposes your manifold into something called chunks, something that used to be just balls above and below the diagram in three-sphere. And these chunks can have complicated topology because you're pretty much almost in an arbitrary three manifold. And you have to think what would be their complexity, what would be the maximal number of tetrahedra you might need to triangulate them. And that's that often comes as an extra parameter if you want just write universal bound for the number of surfaces, but it's also known for many three manifolds. So the upper bound for number of genus G surfaces, orientable or not, possibly with boundary, and with fixed orientable or non-orientable genus G, embedded in weakly generalized alternating link, is now just this, where X is that number of tetrahedra that may be required to triangulate the chunk. So again, we do know what X is for many families of manifolds. But again, the benefit of this bound is that it's universal, it's polynomial, and it's explicit. There are no unknown constants, you know exactly the function. There's been other work slightly before this, by Donfield, Gurfilitis, and Rubinstein, where they give you exact number of disconnected surfaces, which is an upper bound on the number of connected surfaces for many link complements, and for many manifolds. A manifold has to satisfy some restrictions, but it's still a wide family. And they actually have quasi-polynomial in terms of genus. So this can be compared here. We have exponential in genus, but polynomial in number of crossings. But there, the way this works is that you fix a manifold, and then algorithmically you can compute expression. And one can prove that the expression ends up being quasi-polynomial for all but finitely many G. Here, however, what happens, you don't have to fix a manifold. You just have bounds. It works for all manifolds as one formula. And you really capture what it depends on, what the number of embedded surfaces depends on. So it depends on certain topological parameters of the surface and of the manifold, and they're quite simple. So these are a number of crossings when you project on the surface your cusp torus. These are number of tetrahedra in your chunk, and this is your genus. And all these theorems also hold for the infilings of these cusp manifolds for all but finitely many slopes. And what, again, the key here is this extension of standard position. Hovey and Jessica Purcell also called it, Josh Hovey and Jessica Purcell also called it normal position for this cusp, wide family of cusp manifolds. But we also use some geometry. And, here you take this intuition from alternating links and you apply it to a very wide family of manifolds. And it turns out you can take it in a way even further. But first, let me tell you maybe when this bound gets simple. When you, and of course, we had other bounds with Hess and Thompson for classical alternating links, but we only had them for surfaces which are either spanning or ciphered. So you couldn't kind of go around a link multiple times. You couldn't have a boundary with complicated slope. So now this gives a corollary for classical alternating links. You can take arbitrary slope. You can go as many times as you want, with the boundary around the link, and you get a simple bound. And that was previously not known. If your projection surface is a Higard torus in length space, or in a thickened torus, or in a solid torus, that parameter T also goes away. It's a universal constant. And then if your three manifold is actually thickened projection surface, and the surfaces are orientable, like it happens in virtual links, toroidal links, etc., that constant T also goes away. And that bound just becomes a simple expression that depends only on the number of crossings and genus of the surface. And to take it further, it turns out you can use the same intuition and generalize it to all hyperbolic three manifolds. But on one hand, you're using the same intuition. On the other hand, once you move to the realm of all hyperbolic three manifolds, your technique becomes quite different. First of all, you want to look at closed manifolds now. So you cannot just take, cusp torus and project it and think about number of crossings. Instead, you have to think about triangulation. But second, you have to do more geometry in a way. The geometry we did for weakly generalized alternating links was something like Gauss-Bonnet, and then maybe again taking it a teeny tiny bit further. But once you work in a hyperbolic stream manifold, you can actually use differential geometry, and that allows you refine the standard position. So let me talk a bit about that. Sorry, I went back instead of going. Sorry. Just one moment, my slides got stuck a bit. All right, so this is joint work with Lakenby. So it turns out that if you take a general stream manifold, you can hyperbolic stream manifold, you can write a bound with the number of surfaces in terms of hyperbolic volume, and it will be polynomial in hyperbolic volume. It will be universal in the sense that it will be the same bound for all stream manifolds. So the way you formulate it is that there are constants C1 and C2, and they are independent of the manifold with the following property. If you have an orientable hyperbolic stream manifold with finite volume closed to with cusps, then the number of properly embedded essential surfaces close to this boundary in this manifold with Euler characteristic at least chi up to isotopy is at most constant multiplied by volume to constant multiplied by Euler characteristic. And this is polynomial in volume. This is exponential in Euler characteristic. So if you compare this, for example, with Kamin-Markowitz result, there constant depends on the manifold. Here constant is universal, so you really have one bound for all hyperbolic stream manifolds. Constant only depends on Margulis constant, which is the same for all stream manifolds. And in a way, this is, I guess, surprising. And this holds for hyperbolic links. You know, your manifolds could be close to cusp. In hyperbolic links, you would substitute volume with the number of crossings, because roughly volume is the number of tetrahedra. Number of tetrahedra is roughly the number of crossings. I mean, you have to be a bit more accurate, but you still get something like a constant by the number of crossings to the constant multiplied by Euler characteristic. And this is perhaps reminiscent of the results in dimension 2, you know, going one dimension down in 2008. Mirzakani counted simple closed geodesics on a complete hyperbolic surface of finite area. And the way she counted them is that she found relationship to volume of the moduli space of that surface. So in a way, you had a count in terms of volume. Of course, it's a different volume, something related to Will-Peterson metric, but here you get just straightforward hyperbolic volume of that stream manifold. And it gives you a very maybe explicit description what number of surfaces is like, and it also allows you to connect in a way geometry and topology, because when we talk about number of embedded surfaces, we think really about the manifold topologically, but volume is geometric invariant. And maybe let me say a little bit about the proof. Let me check how I'm doing on time. Right, so maybe a couple of minutes. So what's interesting, intuition for this result still comes from alternating links and standard position for surfaces, and 80s and Minascus and Thistlethwaite work. But the methods themselves become very different because we're working with very different objects. And the basic intuition here is that you want your surfaces to be transversal to something, and their transversality is achieved to link diagram, right? And back in the 80s, back in alternating links. Here, transversality is now to a triangulation, because your manifold might be closed. And this, of course, kind of suggests using normal surface theory, because normal surface theory is based on transversality. But normal surface theory, as we saw alone, it doesn't give you any polynomial bounds. It gives you a bound which is tower of exponentials. So what you can do, you can kind of refine normal surface theory by using differential geometry, by using stable minimal surfaces. And minimal surface theory is, its own thing in differential geometry. There's a lot of theorems and facts that have been proved about stable minimal surfaces, about their curvatures, about their area growth, etc. So they're very nice to work with. And what you're trying to do, you're trying to make your surface, on one hand, kind of normal, so transversal to triangulation, and on the other hand, you also try to keep it stable minimal so that it has this very nice geometry. And it's almost like a geometric refinement of normal surface theory that allows you a much closer control of what's going on with those surfaces. And of course, when we talk about this, we have, if it's a cusp manifold, we have to talk about thin, thick decomposition first. And we have to decompose the manifold into thin and thick part, and all this beautiful blend of normal and minimal surface theory will happen in thick part. And then you have to think about thin part separately. So this is in a joint paper with Mark Luckenby, and a big part of it, where it develops this technique where you refine normal surfaces using differential geometry. And is it time to stop? Is it okay? I think it is, right?
No, I mean, I think we may have some more.
I could mention maybe a couple more ideas that go into the proof if it's okay. Thank you. So how do you achieve transversality of a stable minimal surface to triangulation? So what you do here, you actually, instead of modifying the surface, because if you have a stable minimal surface and you try to isotope it to be normal, you will lose your geometry. It will not be stable or minimal anymore. So instead, what you do, you modify triangulation. So you choose a nice triangulation of a thick part of the manifold, and then you adjust it gradually. You do barycentric subdivision, you do various adjustments. You kind of move your vertices about so that your result, your stable minimal surface, ends up being normal to that triangulation. And you can use something called Thurston triangulation, also something that Breslin was studying in differential geometry. So these are triangulations with at most C-volume tetrahedra, but they're not just any triangulations. What Breslin proved is that you can take such a triangulation and make it fat. So there are no flat tetrahedra. And this is where geometry is used. That's why you use hyperbolic manifold. And what happens when your surface is transverse to such a triangulation? So on one hand, there is a controlled number of intersections. The intersections between surface and triangulation come in certain types, like 7 normal disks in normal theory, but also they pick up some area because the tetrahedra are now fat, so they never flat. And you use it to carefully control the number of pieces, much more carefully than you could with just the normal surface theory itself. And that allows you to basically to get the polynomial count. And there are some technicalities that maybe I'll skip and just stop here. I want to maybe put a list of papers, because what I was talking about scattered across several different papers, so maybe it will be useful if you want more details. Thank you.
Okay, thank you very much for this great talk. And we can now stop recording.